Welcome back to the deep dive. Today we're going deep into the mind-bending world of Principia Mathematica.
Oh, yeah.
And as a philosopher, you're no stranger to complex systems of thought. So
All right.
get ready to decode the intricate notation that Whitehead and Russell use to try and build all mathematics from pure logic.
Yeah.
We've got excerpts focusing on the notation itself,
Right.
its quirks, and how it reflects some pretty profound philosophical ideas.
It's going to be a good one.
It is.
Yeah.
So-
You know, it's amazing how Principia Mathematica, published over a century ago,
Right.
still offers valuable insights.
Yeah.
And for a philosopher, grappling with the original notation isn't just a history lesson. It's
Right.
like a key to understanding the evolution of logical thought.
Okay, so let's jump right in. What's the first thing that strikes you when you look at a page of Principia Mathematica?
Honestly. The dots.
The dots.
They're everywhere.
Right.
Instead of parentheses or brackets. Whitehead and Russell use dots for punctuation and conjunction, creating this unique,
Okay.
almost visual language of logic.
It's definitely a different world from the symbols we use today.
Right.
But how does this dot system actually work?
Yeah.
Is there some kind of secret code we need to crack?
Think of it like a grammatical hierarchy.
Oh.
The number and position of the dots tell you the order of operations,
Right.
kind of like how commas and semicolons work in a sentence.
Right.
A colon, for instance,
Okay.
which is just a series of dots,
Mm-hmm.
has a wider scope than a single dot.
Got it. So the placement of each dot really matters.
Exactly.
Can we see a real example from the text to see how this plays out?
Absolutely.
Okay.
Let's look at this axiom, P-E-Q, E-Q.
Ooh.
As a philosopher, I bet you're already starting to analyze the symbols.
Well, I recognize B and Q as propositional variables.
Right.
And the dot probably represents conjunction,
Mm-hmm.
but that triple dot symbol throws me off.
Yeah.
And then there's the negation.
Uh-huh.
It's like a logic puzzle.
You're on the right track. That triple dot is actually the definition symbol.
Oh.
Remember, in Principia Mathematica, everything is meticulously defined, building on prior definitions.
So this isn't just an axiom.
Right.
It's actually defining conjunction itself.
Exactly.
Let's break it down. PQ means P and Q.
Right.
And it's being defined as, what exactly is ick?
It's essentially saying P and Q is logically equivalent to not P or not Q.
Okay.
Remember, this was written before the modern symbols for and or were widely used.
So they're defining conjunction using negation and disjunction.
Mhm.
It's interesting how they build complex concepts from simpler ones, step by step.
Exactly. And those dots guide our interpretation.
Okay.
The dots around the definition symbol have the widest scope, enclosing the whole formula.
Right.
The dots around the disjunction within the negated expression have a narrower scope.
Okay, I'm starting to get the hang of this dot system.
Good.
But here's a question that's bugging me.
Yeah.
Where are the types? I don't see any symbols for things like individuals, properties, or relations.
Right.
It's all just variables and functions.
That's one of the most fascinating things about Principia Mathematica from a philosophical perspective.
Really?
They intentionally left out explicit symbols for types.
Why would they do that?
Yeah.
Doesn't that make the system even harder to follow?
Well,
How do you know what types the variables are supposed to represent?
Whitehead and Russell believe that logical truths were completely general, applicable to any type of object.
Right.
Their system reflects that universality.
Oh.
Later logicians, like Alonzo Church, actually came up with ways to reconstruct the type system of Principia Mathematica to
Interesting.
make it more explicit.
Okay.
But the original text keeps things very abstract.
So Church added the missing pieces to reveal the underlying type structure.
Ab-
That seems helpful.
For instance, he would represent the proposition Socrates is mortal with something like mortal Socrates,
Okay.
where Socrates is of type individual, and mortal is a function that takes an individual and outputs a truth value.
Right.
This makes it easier to see the relationship between different types in their logical framework.
I see. So the types are there just implicitly.
Yeah,
It makes you really think about the nature of abstraction.
it does.
But we haven't even touched on things like bound variables.
Right.
And that strange shriek notation I've seen.
Yeah.
My brain is already starting to hurt.
Don't worry, those are topics for our next segment.
Okay.
You're doing great. What's fascinating about Principia Mathematica is that the journey of decoding the notation is just as important as the destination of understanding the logical system itself.
Right.
It really challenges you to think differently about the foundations of logic and mathematics.
I agree. and I have a feeling it's going to get even more challenging from here. So let's take a quick breather and then dive back into the world of Principia Mathematica.
Sounds good. You know, as a philosopher,
Right.
you're probably familiar with the idea of bound variables. But in Principia Mathematica,
Yeah.
they take on a whole new level of significance,
Okay.
becoming deeply intertwined with the concept of types.
I've always found bound variables a bit tricky.
Right.
Like, they're placeholders, but also somehow tied to the structure of the entire proposition.
Yeah.
How do Whitehead and Russell approach them?
They make this crucial distinction between real variables,
Okay.
which are essentially what we think of as free variables, and apparent variables, which are the bound ones.
Okay.
This ties into their famous vicious circle principle.
Okay. The vicious circle principle.
Yes.
It sounds a bit intimidating. Break it down for me.
Imagine you're trying to define a set that contains all sets that don't contain themselves.
Okay.
Does the set contain itself?
If
If it does, it shouldn't. And if it doesn't, it should.
Yeah, it's a paradox.
It's a self-contradictory definition, a classic paradox.
Right.
The vicious circle principle helps us avoid these paradoxes
Okay.
by setting up a hierarchy of types.
So the theory of types is like a set of rules to avoid logical traps.
Exactly.
But how does this connect to bound variables?
Think about a statement like, for all x, if x is a philosopher, then x loves wisdom.
Okay.
The x here is bound. Right. It doesn't refer to a specific philosopher, but ranges over all possible philosophers.
Right. It's like a placeholder for any philosopher we could plug in.
Exactly.
Okay.
But according to the vicious circle principle, you can't define all philosophers without putting that concept in a higher type than the individual philosophers themselves.
Right.
Otherwise, you're defining the set of philosophers in terms of a set that already presupposes all philosophers, creating a vicious circle.
So the type of the bound variable x
Yeah.
has to be different from the type of the property being a philosopher.
Exactly.
And like a hierarchy of types ensures that everything stays logically consistent.
Precisely. And this attention to types is crucial to the rigor that Whitehead and Russell were striving for in Principia Mathematica.
Right.
They wanted to build a system where every concept was precisely defined and placed within this hierarchy.
It's amazing how much depth there is
I know.
to something as seemingly simple as a variable. But you know what else is intriguing?
What's that?
That shriek notation they use.
Ah, yes.
It looks like an exclamation point.
Right?
And I have to admit, it's a bit jarring when you first see it.
It is a little strange.
Yeah, yes.
The shriek.
It's one of the most distinctive symbols in Principia Mathematica,
Okay.
in modern notation. It's like adding a subscript to a function to indicate its predicative.
Predicative. Okay, now you really lost me.
Okay.
What does that mean?
Essentially, a predicative function is one that doesn't involve quantifying over higher order functions.
Right.
It's like the ground level of functions, directly relating objects or properties without going up a level in that type hierarchy we were just talking about.
So it's a way of keeping the definition of a function grounded, so to speak.
Exactly.
Can you give me an example of how this shriek notation works in Principia Mathematica?
Absolutely. Let's look at how they define identity,
Okay.
which we would normally symbolize as x, y.
Right.
They write it like this: x equals y, x. X.
Whoa. That's a lot to unpack. Okay, I see X and Y, the definition symbol, and then a string of symbols with the Greek letter and those shrieking exclamation points.
Exactly. You're seeing quantification over all predicative functions represented by that. The formula is basically saying that two things are identical if and only if they share all the same predicative properties.
So the shriek is telling us that we're only looking at properties. Yes.
Find at the base level
Right.
without quantifying over more complex functions.
Exactly.
It's like we're limiting ourselves to the simplest building blocks of logic.
You've got it. It's a way of ensuring that the definition of identity doesn't get tangled up in those vicious circles we talked about earlier.
This whole system is so fascinating.
It is.
But I have to admit, I'm struggling to imagine how they use it to define everyday mathematical concepts, like numbers.
Right.
We tend to think of numbers as straightforward.
Yeah.
But in Principia Mathematica, I'm guessing it's anything but simple.
You're right. It's not simple at all.
Okay.
The way they define numbers is surprisingly complex.
Okay.
And dare I say, elegant.
Right.
But to understand that,
Yeah.
we'll need to delve into their treatment of definite descriptions.
Right.
And what's known as the no classes theory.
Okay. I'm ready for the challenge. Let's unravel these next mysteries. Right. Let's tackle definite descriptions as a philosopher. I'm sure you're familiar with the classic puzzle about the present king of France.
Yes.
And whether he's bald.
Right.
How on earth did Principia Mathematica handle these tricky concepts?
It's fascinating how they used the inverted iota symbol to represent definite descriptions. It's like a shorthand for saying the one and only thing that fits this description.
So instead of saying the present king of France, they'd have a symbol for the, followed by some description to pinpoint this hypothetical king.
Precisely. And to avoid ambiguity, they introduced the concept of scope, which is crucial for understanding those tricky philosophical puzzles you mentioned. Remember how the present king of France is not bald?
Yes.
Can have two different meanings.
Absolutely. One meaning is that there is a king of France who lacks hair.
Right.
And the other denies the very existence of a bald king of France.
Exactly.
It all hinges on what you're negating.
Exactly.
Yeah.
Whitehead and Russell used brackets
to indicate the scope of the definite description. So if the negation is outside the brackets, it denies the existence of the thing described.
So by carefully controlling the scope, they could eliminate ambiguity and make their logical statements crystal clear? That's brilliant.
It really highlights their obsession with precision. Now, ready for another head scratcher?
Oh, boy.
Let's talk about the no classes theory. How can a work dedicated to building up mathematics have a theory that claims there are no classes?
Yeah, it does.
Sounds paradoxical, doesn't it?
It does. It's like saying you're going to bake a cake without using any ingredients.
Right.
How do they pull that off?
It's a clever move, really.
Okay.
They reduced talk about classes to talk about propositional functions.
Okay.
Which, as you know,
right.
are the bedrocks of their system.
Right. Those function templates that can be filled with variables to create propositions.
Exactly.
But how do you get from functions to classes? It seems like a leap.
Take the class of all philosophers. Instead of treating it as a separate entity, they define it using the propositional function.
Right.
X is a philosopher.
Okay.
Then membership in this class just means satisfying that function.
So to say Socrates is a philosopher becomes Socrates satisfies the function X is a philosopher.
You got it. And by doing this, they avoid introducing classes as a new type of object, streamlining their logical system. It's all functions and propositions.
It's incredibly elegant. But all this intricate notation and complex logic makes me wonder, did they actually succeed? Did they manage to derive all of mathematics
Good question.
from these basic principles?
That's a question that has generated a lot of debate. They did derive a significant portion of mathematics, but not without introducing some additional axioms. Like the axiom of infinity for dealing with infinite sets.
And the axiom of reducibility to handle certain types of functions.
So even their system, as impressive as it is, needed a few extra assumptions.
And later logicians, like Kurt Gödel, showed that formal systems like Principia Mathematica have inherent limitations. But that doesn't diminish the incredible achievement of Whitehead and Russell. Their work is a testament to the power of human reason to try and understand the foundations of mathematics and logic.
Absolutely. And even though the notation might seem a bit strange to us now, it's a fascinating window into a crucial moment in the history of logic and the philosophy of mathematics.
It reminds us that even the most abstract ideas can be expressed with symbols. And the process of deciphering those symbols can be just as rewarding as the insights themselves.
Well said. So what stands out to you the most from our deep dive into Principia Mathematica?
For me, it's the sheer ambition of the project and their meticulous attention to detail. It's a reminder that even the most abstract concepts can be analyzed and systematized. And for a philosopher, that's a powerful idea.
I completely agree. It's been an incredible journey exploring the depths of Principia Mathematica.
It has.
And for our listeners out there, we leave you with this. If a system like this, with all its complexity and rigor, can be built, what are the limits of human thought?
Good question.
What other systems might we create to understand the world around us? Keep questioning, keep exploring, and keep diving deep.